Hi everyone, welcome back to Operations Research. Today we will introduce a new topic, network flow models, to you. And later you will see that network flow models are somewhat a bridge between integer programming and linear programming. In some sense, these are a special type of problems that can be formulated as integer programs, and we will show you a property that they can actually be equivalent to linear programs. Anyway, yeah, let's first give you motivations and then tell you the story. So P&G is such a famous company. This Procter and Gamble company, they makes and sells over 300 brands of consumer goods. Many famous consumer goods are under the brand name of P&G. In the past, P&G has thousands of suppliers, over 60 plants, 15 distributing centers, and over 1,000 consumer zones. So you may imagine that because there are so many different types of goods produced and made by P&G, and also they sell those goods to many different places, to many different consumers. So it's very natural that they need to manage item flows over a very large supply networks, from multiple suppliers through multiple distributing centers to multiple markets. There is a supply network which must be controlled by P&G. So in order to optimize those item flows, and LP or IP models certainly help. So up to today, your knowledge about LP and IP should be able to give you a sense that given a specific problem description, you have some knowledge to formulate them into LP or IP so that the solution generated by a solver can provide you some managerial suggestions about decision making. Okay, so the same thing happens to these supply chain network operations. What's interesting is that for such a huge problem, even a usual LP or IP may sometimes get stuck because the problem size is so large. So people start to think about, because these problems are somewhat special, right? They are network optimization problems. So is there any special properties that we may use to solve these kind of special problems? And indeed, the answer is yes. Today we will tell you some special structures of network transportation problems. So P&G did the same thing. They use an OR study to formulate LP and IP models and sees those network structures, and then in each year they may save $200 million per year after that OR study. So today we will also do the same thing. We will tell you what kind of network problems may be solved by our OR approaches. And for the whole story, please see the articles on SEBA or the short story in section 8.1. So let's say some more about network flow models. In general, there are a lot of operations that is to transport items on a network. Some examples are here. For example, we may want to move raw materials from suppliers to factories. After we finish making goods, we may want to move goods from factories to distributing centers, and then from distributing centers to retail stores. And there are so many operations happening each day. If we are not sending goods, we may also want to send passengers through railroads or flights. We may want to send data packets on the internet. We may even want to send water through pipelines. Okay? There are so many different things or people to send through a network in the world. So these kind of problems are certainly pervasive in the world. And that's why they are important and need a specific study. Okay? So probably you can also think about other examples. For example, when postmen they need to send mails, or when delivery service companies they are delivering goods. And there are all kinds of different examples. Today, we will talk you a unified model, which is called the minimum cost network flow model. So in the sequel, we will call them MCNF models or minimum cost network flow models. This model, as we will see, can cover many network operations. So there are all kinds of different network problems, and MCNF can cover a huge amount of them. We'll see what's that. And why do we really care about MCNF is because it has some very nice theoretical properties, and that allows us to solve those problems in a very short time, in a very nice result. Okay, so that's also the main topic today. So today in the lecture, in videos, we don't have time to talk about them, but in the lecture time, we will use examples to tell you how these network flow problems can be extended to inventory problems, okay, project management, job assignments, and facility locations, and so on and so on. Okay, so network flow problems are not just to send items on a network. That's a very important application, but that's not the whole story. There are also many different situations that can be modeled as network flow problems, and we will see them. Okay, so my plan today is first to tell you what are MCNF problems, and then in the later videos, I will tell you how to formulate MCNF problems and what's the special properties we just mentioned. And then I will tell you there are some special network flow models, which are special cases of our MCNF problems. Some of them are actually known to you, okay? And we will see the connections in the last section. So before we really introduce the MCNF problem, we need to first help you to review or preview some terminology about networks. This is part of the graph theory. Probably you learned in discrete mathematics or some related course. But anyway, if you haven't, let's start here. We say a network or a graph is a collection of nodes and arcs. Sometimes nodes are also called vertices, and arcs are called edges or links. Okay? A typical interpretation is that nodes are locations and arcs are roads. So let me try to visualize this. Suppose I give you a network like this. So the first component of a network are nodes. Okay? Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 nodes. And then there must be some arcs on the network. In general, arcs may intersect with each other, and let's treat it as two separated arcs. Okay, so the network can actually be very complicated, but in general, they are just a collection of nodes and arcs. In a network, arcs may be directed or undirected. For the graph I just drawn to you, those arcs are directed arcs, and that means we distinguish an arc from A to B or from B to A. That's different. In that case, we say an arc is directed. So for an arc from U to V, suppose we want to say it is a directed arc. Then we use parentheses to include U and V inside. This notation means an arc from U to V. If it's V to U, we will say parentheses V, comma U, parentheses. When we use square brackets, that means it's an undirected arc. And a better way to say it is this is an arc between U and V, okay, if it is undirected. In this lecture, we will always talk about directed arcs, but many things we talk about today can be generalized to undirected arcs. It's just that we don't have time to talk about it. A network is directed if its arcs are directed. So in this course, basically we talk about directed networks. Finally, some people would like to say networks are directed graphs, and the graphs are undirected networks. Now, some people say that, but anyway, we don't care about it. A path or a route from node S to node T is a set of arcs, one arc, two arcs, up to the last arc. Together, they form a path from S to T. So as an example, suppose here we have 5 nodes, S, V1, V2, V3, and T. Then a path in this case is simply the collection of these 4 nodes. Okay, so certainly this is just one path. This is just one path, and there may be a lot of different paths. Okay, so that's just paths are just collected, a set of connected arcs. In this case, we say S is the source and T is the destination of the path, and of course, direction matters. A cycle, or sometimes called circuit, is a path whose destination node is the source node. Okay, it's not very important in this topic, in this lecture, but it's a common notation. A path is a simple path if it is not a cycle. And finally, a network is an acyclic network if it contains no cycle. Something regarding flows. A flow on an arc is the action of sending some items through the arcs. Okay, so that means if we say I want to have a flow on an arc, that means I want to send something on that arc. The number of units sent is called the flow size. So for different applications, the flow or the flow size may have different meanings. If we are sending goods, then it's the number of units of goods sent is called the flow size. If we are sending water, then we may be thinking about tons of waters. If we are sending people, then it's the number of passengers. Anyway, conceptually, there are something sent on an arc, and that's a flow. A network flow is the collection of all the arc flows. Okay, arc flows. So a network flow is just a plan for making flows on all the arcs. Here, one thing to keep in mind is that when we are talking about a network flow problem, that means we are planning about how to send flows on each arc. We want to decide the flow size on each arc. And of course, that somehow need to satisfy some constraints we're going to tell you. An arc may have a weight, okay? May or may not have a weight. If there is a weight on arcs, we say it's a weighted network. For a weight, that may mean different things. For example, it may be a distance, it may be a cost per unit flow, or it may be different things for different applications. But anyway, an arc may have its weight on a network flow problem. An arc may also have a capacity constraint. That means there may be upper bounds or lower bounds on our arcs, and those bounds are for flow sizes. Okay? There may be a restriction saying that I cannot send no more than 100 units on a particular arc, or I must send no less than, for example, 10 units through a particular arc. Now, there may be upper bounds and lower bounds. A network is said to be capacitated if there is any arc having capacity limits. Okay, just our turn. So now we're ready to tell you about minimum cost network flow problems. Suppose there is a weighted capacitated network. Conventionally, we call it G, which is a collection of V and E. G is the network, V is the set of nodes and E is the set of arcs. Later we will see an example. For each node, there is a supply quantity Bi. When Bi is greater than 0, we say it is a supply node. There are some items that will be sent out of the supply node. So you think about that are factories or manufacturers. You're going to send products outside from the supply node. If Bi is negative, that means that is a demand node. So it's something like a market. You need to send something into those nodes. Okay, so that's the situation with demand nodes. If Bi is 0, that means there's no supply and there's no demand. It's just a transshipment node. That means it's just some distributing centers, or that's just some intermediate places for you to stop or change your routes. One important thing here is that for minimum cost network flow problems, we assume or we require that all the total supplies and the total demands must be identical. Okay, so sum of all the BIs must be 0. So this assumption, later you will see that it is required for our formulation to be feasible. Okay, but it's not a very strict assumption because there are always some ways for you to translate a problem whose total supply does not equal to total demands into this situation. Okay, we will also see examples, but keep in mind, when you are asked to formulate a minimum cost network flow problem, you need to make sure that the sum of supplies must be equal to sum of demands, so that for each unit, there is the starting point and there is the destination point. Nothing will be wasted. For each arc, the weight means the cost for each unit of flow. Here, we are saying that the cost is linear. Sending 1 unit cost you Cij, sending 2 units cost you 2 Cij, and so on. Okay, weights are costs. And then the problem is, we have these supplies and we have these demands. How may we send items through our network to satisfy all the demands and in a minimum cost manner? Okay, we want to minimize the cost for satisfying all the demands, and we're talking about operations on network. So this is called the minimum cost network flow problems. We want to minimize cost while satisfying all the demands from a set of supplies to a set of demand nodes through a capacitated weighted network. So an example is here. In this example, there are 5 nodes, right? On each node, there is a label Bi, which means the supply quantity. So node 1 has a positive supply quantity. This is a supply node. Okay, there's one supply node. For node 2 and node 3, they are transshipment nodes. And for node 4 and node 5, they are demand nodes. For each arc ij, there is a label uij, vij, cij. So for example, here you can see there are 15 and $4. That means uij is an upper bound of flow size, and the cij is the unit cost of flow. Here, when we do not write it down, that means all the lower bounds of a flow is negative. Is 0. Okay, so you cannot send a negative number of units on an arc. When we do not write it down, we mean that the lower bound is 0. But when we write it down, then that number means an upper bound. Some arcs may have unlimited capacity, like here. This notation is saying that from 2 to 3, there is no capacity limitations. Okay? Between 2 nodes, there may be 2 arcs of different directions, like here. You may send items from 3 to 5, and you may also send items from 5 to 3. You probably are thinking why it is possible to send in both directions. But when the network is complicated enough, when the problem is uncomplicated enough, this may be possible. Okay. So now, for this particular problem, let's look at it again. We want to send from node 1, in total 25 units, to node 4 and node 5. There are 10 units demand here, 15 units of demand here. Each arc has its own capacity and unit cost. So before we find an optimal flow, let's try to see whether there is any feasible flow. So one example is like this. Let's try this. How about sending through arc 1, 2 for 15 units? Well, I'm not sure whether it will success, but let's try it. Okay, after this, I can send through arc 2, 4 for 10 units, right? That's something I may do. And then for node 4, the demands are satisfied. I still have 5 units unused on node 2. So how about this? Let's send it through this arc. And then on this arc, I can send these 5 units. So for node 5, I still need 10 units to be satisfied. So certainly one thing I may do is to send through these 2 arcs, right? For 10 units. So this particular plan can satisfy all the capacity constraints while satisfying all the demands. Okay? And more importantly, at node 2 we can see that the amount of flow sending into node 2, 15, equals the amount of flow sending outside from node 2, 10 and 5 together gives me 15. Okay, so this so-called flow in equals flow out constraint will be required for the general MCNF problems. For node 3 is the same thing, right? Flow in equals flow out. For demand and the capacity as demand and the supply nodes is certainly not the case, but conceptually it's still the same thing. There are 25 units initially. That means there are 25 units flows in, and then 15 and 10 flow out. For 4, 10 flow in and 10 flow out. Demand are something like an outgoing flows. Okay, so for this particular network flow, we decide the flow size of each arc. For some arcs, the flow size are 0. Okay, these are 0. So we can calculate the total cost. For here, 60. For here, 20. For here, 15. For here, 30. And for here, 10. Summing all of them gives me a cost. And we are asking whether there is another way to sending flows so that the cost can be further minimized. Okay, that's the introduction of MCNF. Later we will talk about LP formulation. Thank you.